today's my topic is to show you this experimental result and simulation of this experimental result. And timeless motion dust particles from magnetic field, stuff like that. And the dust particles in the magnetic field is one of the interesting topics in the dust diffusion theories. In many cases, using magnetic field, researchers using a uniform, strong magnetic field to magnetize the dust particles. But in my case, the magnetic field is very weak, non-uniform, but asymmetric. So, in such a non-uniform magnetic field, dust particle shows a very interesting behavior. So, my purpose to today's presentation is to review my previous work. It's published in 2016, and let's construct a new simulation code to show that experimental result. Experimental devices like this one. There are 3 electrodes: polar electrode, grounded electrode, and confined electrode. These electrodes are connected to the power supply and are 13.56 megahertz and 5 watts. And each electrodes are separated in 15 millimeters each in vertical direction. And there's 100 millimeter holes in the power electrode and confined electrode to see the inside from the top. And top power electrode is connected to the mesh grid to achieve the uniform electric field between the power electrode and ground electrode, and keep the see-through from the top. And power electrode and ground electrode is covered with glass to limit the plasma flow to the electrodes. There's a permanent magnet near the grounded electrode. The magnet strength is 0.14 Tesla in its surface. And around the experimental region, it becomes a little weak. And direction of the magnetic field is in upward direction. And that's what dust particles is fed from the dust heater, located here, and that use dust particles acceleration speed 5.6 micrometers. This device is inserted in a glass tube, vacuum glass tube. And our gas used as a gas brake as a generating the plasma, and pressure is about 6 to 8 Pascal. And obtained typical plasma parameters are like this. And electron density is about 10 to 13 cubic meters, and electron temperature is 3 E. And there's a laser light here and illuminates dust particles. There's a camera here, and regular movie or still image. And this typical experimental result, we are seeing that from top view, this black crossing is the mesh grid, and these green dots are the dust particles, and magnet located below this area. And this is a real-time image, and you can see the clockwise rotation inside, and counterclock rotation and outside. And now you see the full collision in naked eyes directly. To analyze the orbit of the dust particles, there are 5 kinds of orbits. One is the clockwise rotation inside, and 2 is the radial radial motion from inside to outside, and third is the counterclockwise rotation, and fourth is radial motion from the outside to inside, and fifth is the counterclockwise rotation outside. And each trajectory dust particles on each trajectory has a zigzag motion. And this is the image from the vertical plane. These gray dots are the dust particles, and this is the reflection from the dust tube bottom. Permanent magnet locates around here. And the dust particle, it is found that dust particle distribute like a reverse truncated hole with a void inside. This is the schematic drawing of the distribution. And blue area is the dust particle area. And inside is rotate and outside rotation. And this is the rotating directions. And red one is the inside and clockwise rotation, and black one is the counter-direction rotation. And around here, the dust particle makes a shear flow. This is the velocity distribution as a function of height and radius. And black dots are the particles located at the outer edge and rotate counterclockwise, and the red one is the clockwise located inside. And both have lights on the two lights. And as a radial function, dust particle rotation, velocity of the dust rotation is lies on one single line. This is the magnetic field profiles. Arrows correspond, length of the arrow corresponds to the strength of the magnetic field, and the direction of the arrow corresponds to the magnetic field direction. When I put the dust distribution on the magnetic field distribution, it is like this. And lower part, dust magnetic field only directed to only one way, but around here, dust magnetic field directed to one is upward and another is downward. This is a schematic drawing the image of the magnetic field direction. And we can see that clockwise rotation is the part here, and counterclockwise rotation is here. So, and the direction of the dust particle rotation probably related to the magnetic field direction. So we must summarize the experimental result is like this. A complex plasma with non-uniform asymmetric fields was generated up by permanent magnet, and dust particle distributed like a reverse truncated cone with the void in its central area. Dust particles at the edge of the cone rotate clockwise and counterclockwise and make a shear flow. So then from here is a new point. When changing a rotational velocity, it is expected that the system becomes unstable and show nonlinear phenomena such as Taylor flow and normal flow. It is, however, hard to change the rotation velocity in experiment. So then we try to develop a simulation code to investigate the effect of the rotation velocity. So there's some various simulation methods such as the peak or molecular dynamic simulation, but idea adopted astrophysics. The three-dimensional simulation results on the motion of dust particles obtained using SPH method will be discussed. We regard smooth particle as a dust particle in this case. Usually, in SPH method, particle is interpreted as a divided fluid element. But here, we directly regard these particles as a dust particles. The simulation code used here was developed based on the source code provided by Nakagi. By giving forced rotation to the inner and outer edges, it's attempt to reproduce the dust motion. An advantageous point to introduce the simulation is flexibility to change the rotation speed and direction. It's easy to change them and allow to explain without dividing puzzle. The basic equation is the incompressed non-Stokes equation. And U is the flow velocity, and nu is the kinetic viscosity coefficient, rho mass density of fluid, deep pressure, and FQ, electrostatic force, and EXT, the external force. This method, the particle simulation, it's possible to ignore the vector term, and these equations are discretized like this. I is the each physical quantity, pi, can be discretized in the following way. And pi is n is the total number of the smooth particles, and w is the Cornell function. And each Cornell function is normalized like this. And using the Cornell function, we can describe the case derivative of pi like this. The Cornell functions that we use here is for a density calculation called 46 Cornell. It has like this function. And for the gradient of the pressure, we use the spiky Cornell. It's like here. And Laplacian of this viscosity for Laplacian of velocity, like this. And the gradient of the electrostatic potential, gradient of viscous Cornell, it has a like this shape. The image of each Cornell and gradient of Laplacian is like this. And for 6 Cornell, gradient is 5 Cornell, Laplacian viscous Cornell, and gradient of viscous Cornell. For using these Cornells and gradient of Laplacian, I calculate the interaction with the particle and the motion of the particles. The way to calculate the interaction between the J's particle and the neighboring particles is always three-dimensional space is divided into equal space grids, and the hash numbers assigned to each grid cube. And the number of particles included in each cube is linked to the hash number. The hash number cube is over cube, which includes J's particle is put up, and the particles included in the 9 grid cubes around this selected cube are used to calculate interactions. The hash numbers represent each time steps. In the experiment, dust particles distribute like this one, and we press this shape is achieved by the non-uniform magnetic field in the experimental case. But as a preliminary simulation code, we idea use the soft wall instead of the magnetic field. Soft wall means the wall has an inelastic coefficient, and the dust particle hit the wall and reflected to the same horizontal plane and reversed area. And at the same time, the particle hit the soft wall, gained the velocity of the wall, and rotated arithmetical direction. simulation in a horizontal plane and three-dimensional image. The axis of the XYZ is little shifted to make the image show clear. And this is typical result of this simulation result. And top one is the rotation velocity of the wall is 0.2 millimeters per second. It's corresponding to the experimental result. And this shows the horizontal motion of the particles, and this is the three-dimensional image. The rotation direction is shown here. And this also corresponds to the experimental results. And by changing the rotation velocity of the wall from the 0.4 to 1 millimeter per second, these values will also correspond to the experimental results. Unfortunately, it's hard to find the difference between by changing the rotation velocity. So but by picking up the particle number in the same horizontal plane, this is a temporal change of the particle number in the whole simulation area. This is the time and the particle number. And starting from the simulation, particle number is decreases gradually, and around this time, the number of particles comes rather stable. And this is the graph showing the rotation speed and the average reduction rate of the particles. Around here, the reduction rate is little changed. I think this advantage reduction rate is one of the indices of the unstableness of the system. So I think that around here the system becomes visually unstable. To summarize the simulation result, simulation code using a smooth particle hydrodynamics method was constructed and obtained simulation result with a relatively shorter time than quick simulation, even using a larger number of particles. This is because in this speech method, we don't have to calculate the Poisson equation. This is the reason we obtained such a result in a short time. Each smooth particle is regarded as a dust particle, and the particle is distributed shape similar to the experiment. Velocities are given to the particle contacted to the wall. The magnitude of the velocities can vary arbitrarily, and in this simulation, it is hard to change the rotation velocity in the experiment. The number of particles included in the horizontal plane is almost stabilized when the time is longer than 70 seconds. Difference in behavior system is not yet observed even when the velocity is changed, but the particle motion, the particle direction is more active than the experiment. This is a new finding. The result required mechanisms suppress the particle motion. The comparison between the simulation and the experimental result is summarized in this table. In the experiment, magnitude is applied, but in the simulation is ignored. Rotation velocity is difficult to change, but in the simulation is easy to change. Particle motion in the experiment is inactive, but in the simulation is active. And there is or something like that, some nonlinear phenomena not yet found in both cases. This is my conclusion. Thank you very much.
is the reason for the void formation in the center? You have a void in that, right?
It's a good question and difficult question. Probably the profile of the electric field.
But your simulation showed a void density, right?
And simulation you have a void, right? In the simulation, void is forced to make by fitting the wall inside. That's why you cannot look into
You
the
are artificially
artificials.
Okay. And in your experiment, are the ions magnetized? What was the Lambda radius for the ions?
Ions Lambda radius is about 5 centimeters or so.
5 centimeters or more, as compared to the size of the rotating plasma, right?
It's larger.
It's larger.
Have you taken into account with your simulations that the plasma conditions will change if you have such a strong magnetic field direct in front of the electrode? So you get some.
You mean in
higher
the
density.
simulation?
In both, in experiment you can't do anything against that, I think, so you have to take that into account in the simulations because you have a higher, probably a higher density, plasma density in the magnetic field and some additional plasma.
You mean it's a pretty simple once again.
Yes, the problem is if you have a magnetic field direct in front of the electrode, you change the plasma conditions. You get an imaging plasma, and maybe you get a higher density inside, so you get some ion, wind, and etc. outside of that region. That is mainly why you get the void. And so, you have to take that into account in the simulations.
But in the simulation, we get the plasma completely. So
yeah, of course. But maybe later on we have to take that into account.
Thank you.
Yes.
I have to do that.
Maybe a second question: how have you measured the electron density in the temperature? You see that?
In the experiment,
Yeah.
but inside the laboratory inside.
Stationary results or just at one position?
Several positions.
Okay. Yeah. So you will see how.
Radio direction, our height.
Okay. Thank you.
Okay. One final question.
Hello. I have wondered in a lot more previous experiments, this shear flow has been generated by even in uniform magnetic field. So do you make any comments why you have taken the non-uniform, specifically the non-uniform magnetic field for this kind of experiments?
Yes, certainly, and then there's a shear flow experiment and when you're using the unifax magnetic field, but by adopting the non-uniform magnetic field, it's easier to achieve the shear, to make the shear flow than uniform, than the case using a uniform magnetic field, I think. So I use the non-uniform magnetic field to apply. That's well.
Okay, let's take the speaker again and all the speakers.